Hi everyone, welcome to this lecture on tissue types and blood composition. My name's Becca and I'm currently a third year at Wadham College, Oxford, and I'm going to be guiding you through this kind of portion of the spec. So just looking at the spec points that we're covering, we have quite a lot to get through, so it's going to be a bit of a whistle-stop tour through kind of epithelia, connective tissues, skin, and then moving on to blood composition, including the cells, the proteins, specifically focusing on sort of antibodies, complement, and hemostasis, as these are kind of the high yield topics for Oxford exams. So as we work through, we're kind of going to have a focus on the Part A content that you need for your MCQs, but then also a little bit of detail in terms of how you can approach a Part B question on some of this content. So looking now at our kind of lecture outline, as I said, this is kind of how we're going to work through this content. So looking first at epithelia then. So what are epithelia? Epithelia are essentially continuous sheets of cells, one or more layers thick, that cover exterior surfaces of the body, line internal closed cavities and body tubes, which communicate with the outside environment. So with this in mind, we want to classify our epithelia in accordance with both cell shape and organization, and this allows us to better understand their function. So in terms of cell shape, we can classify cells as squamous, in which they're flat and plate-like, they're cuboidal, in which they have a similar height and width of cells, or columnar, in which height is greater than the width of cells. So when you're given a histological section of an epithelial tissue, you immediately want to be looking at the cell shapes that you're looking at, and that will help you identify the epithelial tissue. Additionally, however, the organization of the cells themselves is also really important. So we have simple cells, simple stratification, in which we have single layers of cells. We also have stratified epithelia, in which we have more than one layer of cells. However, we also have pseudostratified, and this often catches people out because it appears to be stratified, as you'll see in an exemplar as we go on. However, these cells are actually all one layer, just of different heights. So the key to identifying this is actually looking at the height of the nuclei, and that will give you a clue as to whether it's actually stratified or pseudostratified. We also have another type, which is transitional, which is specific to the urothelium. And this is the epithelia in which the cells can actually change shape in accordance with the volume of liquid that the urinary system is holding. So we can also look at epithelia by function. So they can be classified as secretory, such as exocrine and endocrine glands, absorbative, such as in the intestine, when we want to take in nutrients, and offering mechanical and chemical protection. So a classic example of this is the skin, which is able to protect us from UV radiation, but also from friction as a result of its properties as an epithelia. We also have to consider that some epithelia are also mechanically protective for different functions, such as, for example, in the alveolar epithelium, these epithelia need to be able to withstand the deformation that comes with inhaling air and the expansion of the alveoli. We can also have a look at embryonic origin of the epithelia. So epithelia can actually be derived from any of the three germ layers. For example, ectoderm-derived epithelia is often stratified or pseudostratified, such as the skin, whereas endoderm-derived epithelia is often simple, in which, like I said, one cell layer thick. So this applies to the liver, the small intestine, and the pancreas. We also have mesoderm-derived epithelium, which is also simple, such as the kidney. So looking at a couple of exemplars that often come up in MCQs, we move first to the simple squamous epithelium. So this, as its name suggests, and we can use the classification we just went over, simple meaning one cell layer, squamous meaning disc-like, and you can actually see on this diagram that they have very flattened cells in which the only bump actually appears to be the nuclei. So those are the kind of characteristics you're looking for to identify the epithelium as simple squamous. The location of these epithelia then is endothelial lining of blood and lymphatic vessels, as well as the alveoli of the lungs. These have multiple functions, including diffusion, filtration, secretion, and absorption. Looking next at transitional epithelium, you can see in the diagram on the furthest right that we have a comparison of the epithelia when stretched versus when not stretched. So this is what I was mentioning with the urothelium, with the epithelia being able to accommodate a change in volume of liquid through changing cell shape. So we have much more cuboidal shapes when the epithelia is relaxed versus stretched. And we can see this in the top diagram, the very rounded shapes of the epithelial cells. So like I said, this functions to accommodate changes in volume of fluid, but also these cells protect from urine, the cauterizing effects of urine. Now looking at pseudostratified columnar epithelium. So if we see the diagram on the bottom, this is again a histological section, and you can see the nuclei are at different heights, which may make you think that there are actually 3 layers of cells here. However, this is pseudostratified, and you can see the diagram at the top gives an indication of how these cells may be a lot shorter, but actually, or much taller, and give the impression of multiple cell layers, but actually only be 1 cell layer. So these are typically ciliated, so that may help you identify whether it's pseudostratified columnar epithelium, and they're also typically associated with goblet cells, which we'll cover in a minute. So these are found lining the nasal cavity, nasal sinuses, pharynx, trachea, bronchi of lung, and auditory tubes. The function of these epithelia is often to synthesize and secrete mucus onto the epithelial surface and move mucus or fluid containing foreign particles over the epithelium. So this is the case with the upper respiratory tract, where we want to make sure that we catch any microorganisms, and then through using our cilia, beating in time, we're able to beat this mucus up out of the respiratory tract to be swallowed. And this prevents microorganisms building up in the mucus and therefore causing infection. So with that in mind, we want to look at the specialization of epithelia. So depending on the function that we want our epithelia to have, we will have certain specializations. So I've already mentioned the cilia that are present in the upper respiratory tract. So these are long projections from the apical surface of epithelial cells, which contain a microtubule core and beat synchronously. So these beat synchronously as a result of motor protein dynin, which moves along the microtubule core to enable this movement. And like I said, this enables propulsion of mucus upwards and outwards. Now we look at microvilli, which are found within the intestine, and these are short projections on the apical surface, typically on columnar epithelium, which increase the surface area for absorption of nutrients. They have a microfilament core of actin, and they also allow cells to change shape. Looking now at keratinization, this is a feature of skin epithelia in which cells are increasingly filled with keratin, and this provides a waterproof and protective layer to the more vulnerable lower layers of the epithelia. Looking now at goblet cells, these are specialized cells which secrete mucus onto the apical surface of the epithelia and are found within the upper respiratory tract, for example, and therefore these allow the epithelia to be lined with mucus. Other specializations of the epithelia, so you may have exocrine or endocrine glands. So exocrine glands essentially means that we are secreting mucus onto an external surface. So these may be multicellular or unicellular exocrine glands. So goblet cells, which we just mentioned, are an example of unicellular, whereas sebaceous and sweat glands, which you would find in the skin, are examples of multicellular exocrine glands. Endocrine glands, however, differ in structure because these aren't secreting onto a surface. Instead, they're secreting into the bloodstream, and that allows the hormones that they secrete to actually have global effects on the body and reach particular organ tissues. So these cells, therefore, these epithelial cells that are secreting require rich blood supply, and hence on the diagram on the right, you can see that these cells are actually surrounded by blood vessels in order to carry away any of the secreted hormones from these cells. Looking now at a part A question, I'll just give you a minute to look at the histological section, and then we'll have a look at the questions associated. So looking first at the first question, we see what is the classification of the epithelium with label 3. So immediately you should be looking at those different heights of nuclei and thinking, okay, this is probably pseudostratified epithelium. Then moving to naming the structure labeled in 4, this is actually a goblet cell, and we can see that the cilia, if you look above the structure labeled 4, you can see the cilia, so we're thinking this is ciliated pseudostratified epithelium, and likely therefore to have goblet cells. Looking at the structure labeled 5, this is actually a basal stem cell, so these will divide to replenish any of the lost cells from our epithelia. Looking then at how you would approach a past paper B question, you would want to have a look at some of these past questions, which tend to focus on the respiratory tract or the intestinal tract in terms of looking at epithelia. And the key focus of these questions is often relating structure to function. So you want to make sure when you approach the question, everything you do, every structure you're mentioning, you're thinking, how does that link back to function? And then to get those top higher marks, you want to be thinking, do I have any experiments that prove that that structure links to function? Or do I have any clinical relevance or clinical evidence that also relates structure to function? So I've put together just an example paragraph of how you might approach sort of this kind of question on the upper respiratory tract. So the upper respiratory tract is lined by ciliated pseudostratified epithelium with a mucosal layer. So looking now at the structure's function, we know that it has a rich blood supply. This is in order to warm and humidify the air that is travelling through the respiratory tract. So there we have the structure to the function. We then have a permeable capillary network, and this allows the recruitment of immune cells. This is important because this is a tissue which is going to be receiving air which has been somewhat purified, but is still going to have pathogens and foreign particles in. So you want to make sure that these are being phagocytosed by immune cells to avoid any kind of infection. You want to also then look at the high goblet cell to ciliary cell ratio. So this means that we're producing a lot of mucus, and this means that we produce sufficient mucus to trap particles and microorganisms. So once we produce this mucus, we then need to think about how we're going to move this mucus. So for example, in the case of cystic fibrosis, you have very thick mucus, which is hard to move, and that leads to actually the microorganisms are retained within that mucus and can lead to chronic infections. So you want to make sure that you're moving this mucus out. So ciliated columnar cells, the cilia within these cells are electrically coupled, and this enables you to have synchronous beating of the cilia, producing a mucociliary escalator. So now what I was mentioning with clinical relevance and how you can kind of access those higher marks, now looking at Cartilage syndrome, there are actually mutations in genes encoding proteins which drive microtubule movement. So specifically DNA1 and DNAH5. So this leads to immotile cilia, which therefore aren't able to clear the mucus, and this leads to chronic respiratory infections. So you can see we've now got some evidence which supports our structure related to function. Now moving on to our junction types. So these epithelial tissues and the epithelial cells within them exist together and need to form a kind of a group in which they're all linked in order to have some kind of mechanical and structural integrity. So the intercellular junctions we're going to look at, particularly that are mentioned within the spec, are desmosomes, hemidesmosomes, and adherens junctions. So looking first at desmosomes, we have cell-to-cell connections. This is where intermediate filaments of adjacent cells are linked. And so this occurs through these intermediate filaments linking onto anchor proteins, such as plakoglobin and plakophilin. And then these desmosomes are linked through cadherin family adhesion proteins, such as desmoglein and desmocollin, which associate to anchor the cells together. So looking then at having some clinical relevance to support our cell-to-cell connections, our cell-to-cell connection desmosome evidence, we have clinical relevance of pemphigus, which is an autoimmune condition in which antibodies are targeted against desmoglein proteins, and this reduces the adhesion between epithelial cells and therefore leads to blistering of the skin and other tissues because you no longer have this tight junction keeping our epithelial cells together. So in a similar vein, we have hemidesmosomes, which again are using intermediate filaments within the cells. So these are proteins such as keratin, but instead of connecting cells to cells, these actually connect the cell to the basement membrane. So you're providing another structural support in which the basal cells of your epithelia are going to be attached to your basement membrane, ensuring that they are secure. You also have adherence junctions. So these are again cell-to-cell connections like desmosomes. However, these use actin filaments, in which actin filaments are connected from one cell to that of an adjacent cell. So those were kind of our anchoring junctions. Now we have some functional junctions such as gap junctions, which are involved in actually the intercellular communication between cells. So these are allow ions and small molecules to pass between adjacent cells. And so these gap junctions are actually made up of 6 transmembrane proteins called connexins, which make up one connexon. And then 2 connexons meet to form a kind of aqueous channel, which enables these molecules to travel between the cells. So this enables you to have a syncytium of cells in which they're all connected and communicating. We also have another type of junction, which is tight junctions. So these are formed, for example, through occludin interactions of proteins, and these are actually really important in determining paracellular transport. So this is the transport of solutes, etc., through or between cells. So you want to make sure that the leakiness or tightness of these tight junctions is associated with the function of your tissue. So for example, in the blood-brain barrier, you want to make sure that you have very tight junctions because you don't want any kind of any material from the blood traveling through the blood-brain barrier, whereas you might have more leaky junctions, such as in kind of endothelium normally, because you don't, it's fine to have actually cells and proteins, etc., traveling from the blood into a tissue. Okay. So now looking at the basement membrane. So this is actually the boundary between the epithelium and connective tissue. So it serves as a barrier between these tissues, both in terms of diffusion of molecules. So you don't want diffusion of your connective tissue molecules, such as glycosaminoglycans, across this barrier. So the composition of this basement membrane is that there are sheets of extracellular matrix proteins such as collagen, in addition to glycosaminoglycans produced by either the epithelial cells or the connective tissue. So a lot of people use basal lamina and basement membrane interchangeably, and actually you need to be careful because the basement membrane is made up of not just the basal lamina. You can see here it's also made up of the reticular lamina. So just be careful when you're using those terms that you're using them correctly. So as I mentioned, it functions as a diffusion barrier, but actually it also functions as an adhesion aid. So as we mentioned with cells adhering to the basement membrane, this provides an anchor so that these cells are firmly attached and the rest of the epithelia are firmly attached to the basement membrane. They can also regulate cellular organization, differentiation, and growth within the epithelia. Now looking at the polarity of epithelial cells. So epithelial cells do not have a constant distribution of ion channels, etc., all the way across the cell. Actually, they have a basolateral domain, which you can see highlighted in red, and an apical domain, which you can see highlighted in purple. And these are separated by our tight junction, which we mentioned earlier. So our apical domain is involved with communication with the lumen or the external tissue. So we're looking at features such as ion channels and carrier proteins, and this enables functions like protection, secretion, absorption, and nutrient uptake. Whereas our basolateral domain has features such as junctional complexes to attach cells to adjacent cells, ion channels, and receptors. So this enables the cells to communicate with each other and also with the basement membrane. and so it has a role in adhesion and communication. Now let's have a look at these next part A questions. So first, cell-to-cell junctions that are primarily responsible for linking keratinocytes in the prickle cell layer of the epidermis. So this is in fact desmosomes, as we know that they are linking two cells together. So it's either going to be our desmosomes or our actin-associated adherens junctions. And in this case, it's desmosomes because those are going to be the primary junctions. Those are the most common ones within the skin. Now looking at naming the primary junctions that attach the epidermis to the underlying basement membrane. So this is going to be our hemidesmosomes because we're connecting a cell to a basement membrane. Now again, name the major mechanical link between adjacent epithelial cells. So you could go with adherens junctions or desmosomes because they both link adjacent cells, but the keyword here is major. So you want to make sure that you're going for the desmosomes as these are the primary junctions. So that draws our section on epithelia to a close. So now we're going to have a look at connective and skeletal tissue. So just to give you an overview, connective tissue, our key players within this tissue are our cells, which are either resident or migratory, and our extracellular matrix, which is composed of fibers which support an anchor, and as well as macromolecules. And the extracellular matrix is often secreted by our resident cells within the connective tissue. Now, connective tissues are all going to be specialized to function. So, for example, you wouldn't have in cartilage a calcified matrix, but where you need that very high strength, you would have the calcified matrix in bone because you don't need the flexibility that cartilage has. So it's worth talking about connective tissues in the specific context to which they're acting because they will have specializations for function. So looking at extracellular matrix composition. So as I mentioned, this is going to be a combination of our proteins, which are anchoring and providing structure, and our macromolecules, such as glycosaminoglycans. So looking first at our proteins, the spec specifically focuses on collagen and elastin. So looking first at collagen, this is the main protein of the ECM. You have many different subtypes of collagen, however, and these will feature differently depending on the type of connective tissue we're looking at. So for example, within the bone, it's largely type 1 collagen for structural integrity. So collagen is actually formed of repeated glycan-containing motifs in a chain, and 3 of these chains will associate to form collagen fibers. It's key that we have glycine-containing motifs because actually forming these triple helices, there's very little space in the interior of that helix. So you want to make sure that it's a very small amino acid that's able to fit within the interior of that helix. And in this case, only glycine is appropriate for that. So these collagen fibers that we've formed, so these triple helices, will then assemble in a staggered formation to form a fibril. So you assemble in a staggered formation and they'll self-assemble because that ensures that you don't have sort of starts and stops. You have lots of overlapping sections, and that will give it a high tensile strength. So now looking at our elastic fibers, so elastin is able to stretch and recoil depending on the connective tissue state, and you'll have associations through through junctions between these fibers, which are found in the lungs, skin, blood vessel walls, etc., where you need a high degree of elasticity. So such as in blood vessel walls, you'll need elastin to be able to withstand high blood pressures and be able to deform, but then be able to retain shape after the deformation occurs. So then looking at our glycosaminoglycans, so these are long unbranched polysaccharide chains which are highly negatively charged, and these often associate with proteins. These attract sodium ions and water, leading to swelling of the ECM. So if you see that your extracellular matrix is very hydrated, you know you're going to have a high presence of these molecules such as glycosaminoglycans that have a high osmotic draw and power because they're going to be able to draw in water and retain it to ensure that the tissue is hydrated and that it's able to resist compression. So this is really important when we have joints, where you need to have be able to have a hydrated gel that's able to resist compression, to resist the weight of the body, essentially. So now looking at cell types in soft tissue. So I mentioned earlier we have our resident and our migratory cells. So resident cells include fibroblasts, which, like I said, secrete molecules that make up the ECM. We also, in specialized tissue, such as adipose tissue, may have adipocytes, which serve as storage for triglycerides. So in adipocytes, as they develop, you'll see that fibroblast-like precursor cells will accumulate these lipid droplets, which grow and fuse together until you actually end up with a cell that is primarily lipid droplet, and actually the nucleus is pushed to the side because these are primarily storage cells at that point for our triglycerides. So you also, however, have migratory cells into the connective tissue. So this includes macrophages, which will phagocytose dead cells and degrade ECM, but also mast cells and lymphocytes, which are involved in inflammation and adaptive immune responses, respectively. So looking at our dense connective tissues now, we have bone and cartilage. So both bone and cartilage are dense connective tissues, however, they differ in mechanical properties. So like I was mentioning earlier, you'll have different compositions of your connective tissues depending on the functional aspects of those tissues. So in bone, bone is rigid as a result of calcification of the extracellular matrix, whereas cartilage is able to withstand compression, but also has some degree of flexibility. So looking first at cartilage, we have 3 different types of cartilage that you need to know about. So hyaline cartilage, to start with, is often described as glassy looking because it's very hydrated cartilage, which has a smooth articular surface. So you'll find this at joints and also flexible parts of the rib cage, the trachea, the bronchi, and the nose. So the composition of this is collagen type 2, which allows a high strength, but also you have GAGs and hyaluronic acid. This leads to a charged but hydrated matrix, so it gives you the gel that's able to withstand a high degree of compression. Looking next at elastic cartilage, so this cartilage has strength and elasticity to maintain the shape of the structures. It also has a network of elastic fibers. So for example, there's the external ear and the epiglottis, which use elastic cartilage. Looking next at fiber cartilage, the properties of this cartilage is that it's the strongest form of cartilage. So in this case, the collagen fibers are actually orientated in the direction of functional stresses to ensure that you're maximizing the strength of your cartilage. And this is present within intervertebral discs, so within the spine, and intra-articular discs in synovial joints. So again, where we need a high degree of strength, and tendon attachment to the bone. So growth of cartilage then, the ECM is first secreted by cells called chondroblasts. So as the chondroblasts secrete this ECM, they actually become trapped within the secreted matrix, and this leads to them becoming chondrocytes. So those are our 2 sort of key cell players within cartilage. Cartilage is actually avascular, so it doesn't have a blood supply in terms of vessels perfusing the tissue. So actually nutrients and oxygen are received through diffusion, and this is going to limit the maximum thickness of our cartilage. It's actually, if the cells aren't receiving enough nutrients and oxygen, they'll die. So this actually limits how thick our cartilage can be. And growth of cartilage can actually occur in 2 ways that you need to know about. So this is interstitial growth, in which our chondrocytes divide and produce new matrix within your existing cartilage. But also you can have appositional growth, in which new cartilage is added to the surface of older cartilage by new chondroblasts. So our chondroblasts are our cells which haven't been surrounded by matrix yet. And these are from the perichondrium, which is actually a layer of connective tissue which covers the surface of most cartilage, but is not present at our articular surfaces. So now here is a part A question to have a go at. I'll just give you a minute on that. So the cell type that makes cartilage is actually our chondrocyte. Whereas when we're looking at the second question, which of these is a hydrated molecule which reduces friction at joints, that's going to be our proteoglycan. The key here is we're looking at a hydrated molecule, and we know that that's going to be a proteoglycan because, as I mentioned, that draws in water due to a high osmotic pressure coming from those proteoglycans. So now moving on to our other connective tissue that we'll be looking at in detail. This is bone. So the ECM of bone is composed of collagen, type 1 collagen this time, which provides tensile strength. So actually, if you denature the collagen within bone through applying heat, you'll find that the bone is really brittle. So we can tell that it's providing tensile strength. Whereas we also have hydroxyapatite. So these are crystals that are actually deposed into our ECM, and they attach to collagen fibers to provide compressive strength. So if you actually dissolve these crystals using acid, you'll find that bone is bendy, and you're able to actually bend it in all kinds of shapes. So that kind of shows that that's providing a lot of the structural integrity of the bone. However, there are also proteoglycans and elastin present within the ECM of bone. The cellular composition then is more complex than our cartilage composition. So we have osteoblasts. These secrete osteoid, which is the organic component of the bone, and which is rapidly mineralized by the deposition of these crystals, which we mentioned. We then have osteoclasts. So these are involved in bone remodeling, specifically in resorption of bone through acid and protease secretion. And we'll get on to a bit more on osteoclasts in a minute. Osteocytes are surrounded by bony matrix and connected to other osteocytes by cytoplasmic processes which extend into canaliculi. So canaliculi actually enable the cytoplasmic processes between different cells which are actually separated by fully ossified calcified matrix to connect together, and they're able to actually have gap junctions between the cells. And this produces a network of force sensors, and this means that your osteocytes are actually able to tell where there is more force being put through the bone, and this can inform the sort of tissue remodeling steps that occur in terms of reinforcing the tissue to ensure that there isn't excess deformation in any particular direction. So look, there are several different types of bone connective tissue. So looking first at compact bone, we actually, this diagram on the right shows you the kind of composition of a single unit of compact bone. So compact bone will be made up of many of these concentric circles. So kind of just looking at the structure of this, so this unit is called an osteon. And so we can see in the middle, we have the Haversian canal, which has the actual blood supply for this particular osteon. So you'll have your artery and your venous supply. Then surrounding this, you have your lamellae, which are in concentric circles. So this is actually your collagen fibers running in different directions. And you also have within these your chondrocytes. So these are embedded within and will be connected by the canaliculi, like we were mentioning before, and communicate through gap junctions. And these canaliculi also allow these chondrocytes to receive some nutrients, so they don't, so these cells don't die. So this structure, although very effective in terms of providing strength, they're actually very dense, and we need to have bone that isn't too heavy. Otherwise, we wouldn't actually be able to move our limbs because it would actually be too heavy and too much stress on our muscles moving the limbs. So we actually have a lot of trabecular or cancellous bone. So whilst our compact bone will make up the outer shell of your bones, for lightness, you'll then have trabecular bone within the centre or within the outside before you get to the sort of bone marrow centre. So these are found in the interior and the epiphyses of long bone, and actually contains many interconnecting cavities in which you'll have compact bone at right angles, so that you're able to have a lot of resistance to force within these trabecular cancellous bones. You also have the periosteum, which is a dense fibrous layer on the outside of bone, and muscles insert onto this layer. And it contains our bone forming cells, which are our osteoblasts. Finally, within the very center of your diaphyses, you have your marrow cavities, which are there for hematopoiesis and fat storage. So a very common question that they like to ask for part B is about the growth of long bones. So I've got a diagram here to kind of summarize the process, but essentially when you first form your long bones, they actually form a cartilage model of the bone. And then first at the outside of the bone, as we can see in sort of the first diagram on the left, you have the periosteum growing around the cartilage, in which osteogenic cells differentiate into osteoblasts and secrete your osteoid. So you get, there's a lot of O's going on there, but essentially you get ossification of the outer collar of your cartilage model. Then within the center of the bone, you have a primary ossification center. So this ossifies the inner cartilage, and this means that actually nutrients, like we were saying, cartilage, you can only have a certain thickness, and these cells need some kind of sort of support in order to survive. So actually once you have bone deposition, the cartilage starts to die because it's no longer getting the nutrients it needs. So you'll have cartilage deterioration and ossification in the center of the bone. Then you'll have blood vessels invading. So as a result of VEGF and other pro-angiogenic factors, you'll have your blood vessels invading the inner cartilage alongside nerves and osteoblasts and osteoclasts, which are coming in from our outer collar here and are traveling into the center of the bone. So osteoclasts serve to break down the remaining cartilage. So those are our cells that are secreting acid and proteases. So those are able to break down the cartilage extracellular matrix and enable osteoblasts to then secrete osteoid and then subsequent crystal deposition to produce what we know as cancellous bone within the middle of these bones. So then finally, you kind of have this process expanding, as we can see in sort of the fourth diagram from the left. This process expands up the diaphyses, and we get to our epiphyses. And these actually remain as cartilage rather than ossifying immediately, and we then get formation of a secondary ossification center. And this is very similar to our process that occurred within the center of the bone. However, no compact bone is formed, and layers of hyaline remain on the ends. So hyaline is our articular cartilage. We also have the kind of divide, as you can see in the light yellow on the final diagram, between our epiphyses and our diaphyses will remain as actually cartilage, so that we don't have, or it will remain unmineralized, so that we're actually able to grow the bone until adulthood. So now that we know that there's a sort of location of bone growth occurring throughout childhood and into adulthood, let's have a look at how these cells actually divide to increase bone length during growth. So we actually have several zones here, and this is a very common Part A question, where they like to ask you which zone you're in. So the key is kind of looking for the key features within each one. So we can see in number 1, we have our zone of resting cartilage. So this is where your cartilage attaches to the epiphyses, and you can see that there's fairly sparse cells there, compared to then our zone of proliferation, in which you have new cartilage forming as chondrocytes and dividing through mitosis. So you can see really dense stacks of cells in our section number 2. Then looking at number 3, we have our zone of hypertrophy. So this is where chondrocytes mature and enlarge. So you can see that these cells are becoming a lot larger, a lot more circular. So that's what you're looking for to identify that region 3. Then you have the zone of calcification, in which matrix is calcified and our chondrocytes die, because once they're not receiving the diffusion of nutrients they need, they will die. And then finally, we have our calcified our ossified bone, in which the cartilage is calcified and replaced by bone. So we have our matrix is fully calcified, and we'll have our osteoblast moving in. Okay, so now moving on to sort of the remodeling of bones. So although we've talked about how long bones develop initially and how they grow through to adulthood, we actually have constant remodeling of our bones, because bone is fundamentally a dynamic tissue. It's often thought of as a very static thing, but actually we need constant resorption and formation to reinforce areas that are under high stress. And like I was mentioning earlier, when we have those canaliculi and those gap junctions between our osteocytes, they're able to sense where the force is and therefore where needs reinforcing. So in essence, in order to remodel the bone, osteoclasts first move in and remove bone, followed by osteoblasts forming new bone. So the key points in terms of resorption that you need to know for your exam is essentially that through a proton pump, you have the secretion of H+ ions. And this is into an area that we call the Hauschilp's lacunae. And this is essentially where we have our osteoclasts. I don't know if you can see the pink little X's there on the diagram on the left-hand side are actually integrins. So this means that we have a really nice sort of, I don't want to call it vacuum packed, but we have a very close association and sort of pocket in which our osteoclast can secrete acid and not damage the bone surrounding. So it very specifically secretes acid into this section of bone that we're trying to remodel. And it will also secrete chloride ions as well as proteases. So therefore we're able to break down the matrix and kill any cells within that area. And then we also have the proteases that are released by these osteoclasts, releasing signaling peptides to stimulate the osteoblasts to fill holes. So it's no good us just having constant resorption of bone and dissolving all our bone with acid. We need to make sure that our osteoblasts are actually moving in to put down new cartilage, to put down new extracellular matrix and new cells. So we need to make sure that this process is always in balance. Otherwise, we end up with what occurs in osteoporosis, in which these processes are off kilter, and it means you have excessive resorption, and therefore your bones get really brittle and at risk of fracture. So the control over remodeling, therefore, is really, really important that balance is right. And this is done by several molecules. So osteoblasts are actually in control of the differentiation of osteoclast progenitors into osteoclasts. So osteoblasts, again, a lot of cells that sound very similar, but so just to reiterate, that's osteoblasts, which are the blue cells labeled with rank L here. So they produce rank L, and this diffuses across to our green osteoclast progenitor and acts on their rank receptor. And this causes the differentiation of the osteoclast progenitor into a fully functioning osteoclast, which is going to go off and resorb bone through, like we said, secretion of acid and proteases. So you want to make sure that there's not excess of that occurring. So in addition, there's also osteoprogerin, which is produced, which by, again, osteoblasts, which inhibits the action of rank L through binding to the rank receptors. So this means that we actually have a mechanism by which we can sort of have a feedback loop between these two products and ensure that there isn't too much bone formation or bone resorption occurring. However, there's also the external factors in terms of hormones that are contributing to this. So we have insulin-like growth factor, which is produced by the liver in response to growth hormone released by the anterior pituitary, and this stimulates long bone growth through acting on osteoblasts. So it stimulates osteoblast activity, so we're going to have greater bone formation. So an example that, if you're thinking about this in a Part B context, where you need some kind of clinical relevance to support your point, an example is Laron syndrome, in which growth hormone's insensitivity leads to signaling defects between this pathway of growth hormone to insulin-like growth factor. And this results in a really short stature because you're not getting this action of osteoblasts, and therefore you're not going to get your bone growth. On the other hand, we have estrogen, which actually stimulates the production, of osteoprogerin by osteoblasts, and therefore inhibits the action of rank L. So we're going to prevent that action of osteoclasts in terms of bone resorption. But actually then, when women no longer produce estrogen or at much lower quantities following menopause, we find that there's much increased bone resorption, and this can lead to that imbalance that I was talking about, which we're really trying to avoid, which leads to osteoporosis, which can lead to that vulnerability, particularly in women that have premature menopause. You want to make sure that you're giving them some kind of supplement for estrogen to ensure that they're not going to get this kind of excess bone resorption. Okay, so now having a look at some Part A questions, we can either put them in the chat or I'm happy to just go through the answers. I'll just give you a second to look at them. So calling all the way back to the beginning of this kind of section, the type of cartilage found on articular surfaces of synovial joints is our hyaline cartilage. Then the cell type which stores large quantities of triacylglycerols is going to be our adipocytes. Then in terms of the cell involved in bone resorption, we have osteoclasts. And finally, the cell which goes by hypertrophy at the epiphyseal plate. So remembering that kind of section we had through the epiphyseal plate, we have chondrocytes which go by hypertrophy at phase 3, or the third section down. Great, so this is just a selection of the Part B questions that kind of tend to pertain to this section of the spec, which is a lot to do with bone growth, but hopefully you would now feel fairly confident in terms of how to structure that kind of argument and the kind of evidence you can bring in clinically to support how bones grow. So just a quick run through some collagen disorders. So when you have, because collagen is such an important part of the extracellular matrix in these connective tissues, when you have abnormal collagens, you'll have reduced function. So in Ehlers-Danlos syndrome, this results in flexible joints, stretchy and fragile skin. In Marfan syndrome, you have a reduction in the production of fibrillin, actually, which reduces the amount of fibrillin available to form fibrils, and you get slim individuals with long limbs and, again, loose flexible joints. Then in osteogenesis imperfecta, a decrease in type 1 collagen, which we know is key within the bone matrix, leads to bone deformities. So now moving on to a particular example of epithelia, skin is often asked about in our kind of Part Bs because it's a great example of many different sort of layers of epithelia having different functions. So the function of our skin is actually largely protective in terms of preventing water loss, preventing infection by microorganisms, preventing damage from UV light. So this is just some examples of our mechanical, thermal and chemical stresses, but also involved in thermoregulation through sweat glands, hair and adipose tissues, and sensation due to nerve cells within the skin. So looking at the composition of our skin, the outermost layer is our epidermis. And you can just see this labeled on our diagram to the right. And this is going to be stratified epithelia because we have multiple layers of cells. And these actually become terminally differentiated into keratinocytes as you move outwards. So by that, I mean, you're getting more and more keratin deposition because keratin is able to strengthen the cell, and you actually get the keratin replacing the nucleus. So you have cells that are completely dead and just a shell containing keratin in essence, which can then be sloughed off, but they provide us with that protection that we need from UV and that waterproofing. So it's a really important process that terminal differentiation to keratinocytes occurs. So then we have our dermis, which is a thick middle layer of dense irregular connective tissue. So this contains collagen and elastin to anchor the epithelium. And you can see the slight undulation here. You'll see it a little bit clearer when we move on to the next slide. But there are these things called Rett ridges, which enable which sort of act as another way to prevent friction sloughing off your entire epidermal layer. You want to make sure that there's a lot of adhesion between your dermis and your epidermis so that your friction isn't going to kind of remove the epidermis. So those undulations help with that. So we also have macrophages present, hair follicles, sweat glands and sebaceous glands. So I'm not sure if I can get up a pointer. No, I can't seem to do that, but essentially you can see the sebaceous gland is just a little sort of nodule off of the hair follicle, and then you can see the kind of bundle structure in blue is actually a sweat gland, and that's receiving quite a high blood supply, which you can see kind of on the left of the hair follicle. And there's also a rich blood supply to the skin. So again, the epidermis is going to be avascular because it's epidermal tissue, so epithelial tissue. But our dermis is going to be richly supplied with blood. So then our hypodermis is our innermost layer, and this is loose connective tissue. So this allows the skin to move over the underlying muscle, and it also contains a lot of adipose tissue. So you can see those little balls of circles of yellow are actually the adipose tissue within our hypodermis. So again, that's going to help with our thermoregulation. Okay, so looking at the composition specifically of the epidermis, there are quite a few cell types that you need to be aware of. So we have our keratinocytes, which I mentioned before, which are our terminally differentiated epithelial cells. We also, however, have melanocytes. So these are actually present, you can see labeled, they're in yellow at the bottom there, which produce melanin pigment within melanosomes. And these are actually transferred to keratinocytes through cytoplasmic processes. So this means we're transferring this melanin pigment, which provides some protection from UV radiation. And then we also have Langerhans cells. So these are tissue-resident macrophages specific to the skin, and these are particularly present within the stratum spinosum. So you can see labeled there, that's kind of our fourth layer down in the epidermis. That's where they're particularly present, although they're present within every layer. And then we have our Merkel cells. So those are mechanoreceptors. So they essentially receive information about light touch sensation and relay that as nerve cells. So looking at kind of the clinical relevance then, you can see that there are quite a few different conditions which result from sort of abnormalities within the skin. So basal cell cancer is the most common form of skin cancer, and this is due to uncontrolled division of basal cells. And we often get epithelial cancers arriving because there is a need to replenish the epithelia so regularly that you're having these basal cells dividing almost constantly anyway, so it's easy for that uncontrolled division to result. We also have melanoma, which is a skin cancer of melanocytes, and albinism, which is where there's a reduction in or absence of melanin biosynthesis by melanocytes, and this leads to risk of UV radiation because you don't have that melanin pigment protecting the skin. And then you have epidermolysis bullosa simplex, which is an inherited disorder in which you have mutations in your keratin. So these are our intermediate filaments. And this means that these particular keratin mutations disrupt hemidesmosome junctions. So this is our junction from our epithelial tissue, as we were saying earlier, from our epithelial cells onto our basement membrane. So it means that you're not going to get that really strong adhesion, which is really important for avoiding friction. So actually you end up with blistering at your epidermis to dermis junction. So now looking at a little part A question to kind of test what we've done so far, just have a think for a second about whether you could label the structures that have been highlighted in this section. So just going through these now. Number 1 is actually a sweat gland. Number 2, we have a sebaceous gland. So we can see again that it's kind of an outpocketing from our hair follicle. Then number 3, is our hair follicle itself. And then number 4 is your outer keratinized epithelial layer. So now looking at kind of a part B question, if they were asking about how the skin is adapted to function, similarly to how we approached the respiratory epithelium question earlier, we want to be thinking about always relating your structure to your function. So I would probably take it each layer in turn. So I've just picked a layer as an example here, the stratum basale. So as I mentioned earlier, we have those rete ridges. So this increases your surface area with the dermis, leading to mechanical strength under friction and shearing forces. You also have your hemidesmosomal junctions, which increase mechanical strength. And again, you can mention your epidermolysis bullosa as your clinical relevance to reach those higher marks in terms of supporting what you've just said with structure and function, in terms of where where this has gone wrong, say where the structure has gone wrong, we can clearly see that it must have a really important function, because we can see that when you mutate those those things that are important in those junctions, you get these consequences such as blistering at that junction. And then I'd also mention the melanocytes that are present within that layer of the skin. Okay, so now moving on to blood cells. So there isn't too much you need to know at this stage in terms of detail on these blood cells. So we're kind of going to do a bit of a quick whiz through these cells. So the first thing to recognize is that there's a blood stem cell, which is located within the bone marrow, which gives rise to both of these lineages. So almost all of your blood cells are going to be derived from these blood stem cells. So the other key thing to note is the proportion of these cells within the blood. So you can see in this box in the right hand corner, I've given you the spec breakdowns of the particular white blood cells within the blood. And these are really easy marks that you want to make sure that you have all of the information on the first page of the spec, which gives you all of the details in terms of these kind of values. You want to have them at your fingertips so that you're not losing any marks over those kind of questions. And in that kind of similar vein, when we're looking at our red blood cell counts, the spec tells us that it's 5 times 10 to the 12 cells per litre. And in white blood cells, it's 7 times 10 to the 9 cells per litre. So then looking at kind of a few details on each of these cell types, particularly the red blood cells. So looking at kind of relating structure to function again. So these are biconcave cells, and this means that you can maximize surface area for diffusion, and that maximizes their role in terms of oxygen and carbon dioxide transport. They also are deformable, so that means that they're able to travel through very small capillaries because they can deform easily, which wouldn't be possible if they weren't kind of that shape and able to deform. And then we also have kind of a bit of clinical relevance there with sickle cell anemia, which is where you have a mutation in your beta globin gene. And that means that you actually get these really rigid rods of hemoglobin, which result in these really hard, they're called sickle shaped, but I would imagine it is kind of a hard C, which means that they're not deforming as they would be. So you actually get clogging within these small vessels, which can cause serious issues in terms of symptoms. So that's just an example of, again, how you can do that structure to function and support it with some clinical relevance. Then kind of moving on from our red blood cells to our white blood cells, the kind of key thing within these is distinguishing them with your adaptive versus innate immune responses. So you can see the cells derived from our myeloid stem cell are going to be our innate cells. So these are our eosinophils, neutrophils, and basophils. So neutrophils are professional phagocytic cells, whereas eosinophils are particularly involved, and they love to ask about this question for some reason, in allergic reactions and in parasitic infections. So that's one to remember. Whereas basophils are particularly involved in terms of activating mast cells, which release histamine. So you're going to get increases in blood flow and vascular permeability as a result. Then moving on to look on the right hand side at our lymphocytes. So we have our B lymphocyte and our T lymphocyte, and these are both involved in our kind of innate, our adaptive immunity, which we're actually going to touch on a little bit more later. So our B lymphocytes differentiate to form plasma cells, which produce antibodies, whereas our T lymphocytes recognize through their T cell receptor cells that are infected and are able to kill them. And they're able to activate B lymphocytes also. So then looking at the next point on the spec, which is being able to recognize these cells on blood films. So this is more likely what you're going to be asked about in terms of Part A questions. So if you just take a second to kind of have a glance at how these cells look. So the key features I kind of want to point out to you. So erythrocytes, which are the majority of the panel on the left, are biconcave shapes, and they resemble donuts. So you can see you kind of have that outer rim of red, and then because of the biconcave shape, less kind of red within the middle. And that's kind of how you can identify them. Then looking at your neutrophils, you have multi-lobed nucleus, and they are granulocytes, so they have granules within them. So you can distinguish these, however, from eosinophils, which are also multilobe, also have multilobe nucleuses, because eosinophils, you'll die with eosin stain, and because of the acidophilic granules within eosinophils, you'll actually get a really brick red stain, whereas your neutrophils will remain a kind of light pink. So that's how you would distinguish those cells. But as we know from the kind of proportions, you're going to get many, many more neutrophils than you would eosinophils in general. Then looking at your lymphocytes, so these lymphocytes, as you can see in this panel that I've drawn an arrow to, have a huge nucleus that takes up pretty much most of the cytoplasm. So that's kind of your main way to identify them. And then monocytes have a nice kidney-shaped nucleus, and they're big. They can be up to 20 in diameter. So that's something to bear in mind as well. Okay, so now moving on to hemostasis. So hemostasis is the process that produces blood clots in order to prevent excess blood loss. So the key stages I've kind of summarized here, which is your actual arterial injury occurring, and that leads to arterial constriction through smooth muscle cell contraction, and that reduces your downstream blood pressure. So you want to make sure that you're getting constriction so that you're not having really high pressure blood going through and therefore losing tons and tons of blood. And also you need a relatively low blood pressure in order to have all of your clotting factors, etc., staying within the same area, because in order for your clots and your fibrils to form, you need to make sure that you have a high local concentration of these factors. So therefore, we need this kind of lower blood pressure. So once you have that constriction, you then have activated platelets. So these platelets are going to be activated, as I've shown in the diagram on the bottom, through interaction with von Willebrand factor. So this is actually secreted by the basement membrane. But obviously, because your endothelium is normally covering the basement membrane, you would never normally have interactions of platelets with these factors. So when platelets do come into contact with von Willebrand factor, that leads to them being activated. And these activated platelets will also interact with fibrinogen. So the binding of fibrinogen, which is shown as these kind of 3 black dots, actually causes a change in the charge of the activated platelets. And this means that the platelets won't repel each other as much as they normally would. And that enables them to get close enough together to form a solid clot. So we have then a platelet plug that kind of forms. And these activated platelets will also secrete or release serotonin and thromboxane. And this maintains your arterial constriction, because actually your initial constriction resulting from your injury only lasts for a very short period of time. So you want to make sure that that constriction and therefore your low blood pressure is maintained for a bit longer. So through serotonin and thromboxane. So then once you have your platelet plug, that's actually relatively fragile. So you want to make sure that that's reinforced with fibrin filament assembly, which reinforces the platelet. And then you can initiate the repair process. So the clotting cascade. This is, again, a real highlight of Part A, is that they like to ask quite a few questions on this kind of thing. So just familiarise yourself really quickly with this diagram on the right, which I've kind of shown you has the intrinsic and the extrinsic pathway. So these pathways are essentially different methods of activating and different factors that are involved, but they both reach the same point, which is our common pathway, and that leads us to our key feature, which is the conversion of prothrombin to thrombin. And then thrombin is able to convert fibrinogen to fibrin, and then fibrin is able to form a tight clot. So fibrin is the key sort of fibre that we want to produce, and so all of the rest of it is only leading to that end point. So kind of think of it as a funnel, and you have different aspects that lead to our common pathway, and then that leads to our thrombin and then our fibrin. So we generate fibrin strands from fibrin monomers, and this occurs through a series of zymogen activations, which I'll show you on the next slide, which acts as an amplification cascade. And we also have positive feedback loops occurring within those cascades. And this is critically regulated because Obviously, with blood clotting, it's vital that you don't have too little clotting, otherwise you'll continue to bleed, such as in the case of haemophilia. But also you don't want too much, because otherwise you're going to end up with lots of little thrombi that are traveling around in your body because you produce small clots for no reason, for no injury. And so those can obviously cause damage in terms of occluding vessels and that kind of thing. So here's kind of a diagram that summarizes the intrinsic and the extrinsic pathway. Now, unfortunately, there is kind of no hack to this. You've just got to write it out a few times, and it will be relatively straightforward. Once you've written it out a few times, you'll kind of get to grips with it. But essentially, the intrinsic pathway, which is on the left, begins with an abnormal surface, so a negatively charged surface, and that leads to the conversion of factor 12 into factor 12A, and we get this pathway in which we have these conversions, so these zymogens, which are cleaved to produce these kind of cascades. And obviously with a kind of enzyme cascade, at each stage you're getting amplification, because one enzyme doesn't just act on one molecule, it will act on multiple. So that's how we get one case of, say, a negatively charged surface then hugely amplified to produce a large clotting response. Alternatively, tissue and vessel damage leads to tissue factor release, and then we can see that that's in the extrinsic pathway, our mechanism in terms of reaching our end point, which is factor 10A, which then converts prothrombin to thrombin. In the green arrows, just to highlight those to you, these are actually positive feedback loops. So thrombin actually acts on factor 8 to increase the conversion to factor 8A, and then therefore factor 8A, which positively feeds back onto 10A, is able to drive that pathway to ensure that we're getting that positive feedback loop, which just maximizes kind of the amount of thrombin we're producing. Just to draw your eye to the kind of clinical relevance of this, so we have haemophilia, which occurs where you have, in most cases, a factor 8 deficiency, and you'll therefore have excess kind of bleeding and lack of clotting. So as I mentioned, you have to really strictly regulate these processes. So the regulators in terms of clot formation, as I mentioned, blood flow is really important, but also there are particular chemicals. So I've just highlighted on this kind of diagram where these particular chemicals are acting. So activated protein C prevents this conversion of factor 5 to 5A and 8 to 8A. Then antithrombin acts on factor 10 and also on thrombin to prevent those factors being produced. And then we also have our extrinsic pathway inhibitor, which acts on our tissue factor and our factor 7. So all of these are just acting to ensure that we don't have excessive clotting, which again, we wouldn't want. Then once our clot has been formed and we're getting healing, etc., and also just to regulate to make sure we're not having excess clotting, we want fibrinolysis to occur. So this is where we have degradation of the fibrin we've produced at the end of this cascade. So plasmin acts to degrade fibrin. But obviously, so plasmin actually circulates in an inactive form, because you don't just want a kind of element in the blood that's constantly circulating, that's able to break down fibrin. So we want to make sure if we're activating and having plasmin act, it's local to the site of clotting. So in order to achieve that, it's actually pretty clever that they have the inactive form of plasminogen with the activator of plasminogen, which is called plasminogen activator handily. This binds to fibrin, and that enables the plasminogen activator to act on plasminogen, producing plasmin, which is able to then break down fibrin. So again, it's all about having the right things occurring over the right time scale in the right location, and that ensures that we have clotting occurring appropriately. So the common questions that I'll kind of ask you within the Part A section is sort of just testing your familiarity with this cascade typically. So again, just writing it out a couple of times will really help with that. So now looking at antibodies and complement. So antibodies are produced by plasma cells, which differentiate from B cells. So I've just put in the transcription factor. Apologies about that. I've just put in the transcription factor, which is involved in this, which is BLIMP1. which converts the B cells to the plasma cells, which are then able to secrete antibody. We then have the antibody structure. So this consists of our constant region, which is highlighted in pink here. So our antibodies, the key kind of aspect of antibodies is that they've got to be really specific to an antigen. So what we want, ideally, is our antibodies to be binding to a particular antigen, a pathogen, presenting a particular peptide. And so we want to make sure that we have complement sort of variable regions so that the sort of different antibodies that we produce are able to recognize a whole range of pathogens. So we have these variable regions highlighted in orange, but we also have these constant regions because actually once we only want one region, the actual antigen recognizing region, to differ, because that's the part that's going to recognize different pathogens, etc. But actually our constant region, which I'm now going to kind of refer to as our FC region from now on, is really vital in terms of interacting with innate effector mechanisms such as immune cells. So you actually want that to be completely constant so that we only need a singular receptor, our FC receptor, to recognize that constant region. So that's why we kind of divide it into our FAB region, which is highly variable between antibodies, and our FC region, which is relatively constant. Now, a mainstay of Part A questions is a real focus on the different isotypes of our antibodies. So I've just put together a summary table here of kind of everything they would normally ask you to do with the different types of antibodies. So just to draw your attention then to just a couple of points on here. So the IgM pentamer, so this is when IgM, which is a particular type of antibody, is often found in a pentamer. And this means that IgM has really high avidity. So avidity is actually where you have binding occurring. So if you imagine my IgG monomer could associate with an antigen, but actually if I have a pentamer in which I have 5 sites that are able to interact with an antigen, I have a much higher avidity because I have a greater chance of a greater strength of association with an antigen. So that's why we have this IgM pentamer. So just to kind of highlight again, another particular feature on this table is that the secretory IgA, which is secreted into mucus and protects the mucosa, is actually found normally in a dimer, whereas our IgG, IgE and IgD are all found as monomers. Just to highlight a couple more functions, the IgG monomer interacts with macrophages and activated neutrophils. So that's what I meant by we have those innate immune system effector functions that are activated by our antibodies. And similarly, IgEs interact with mast cells. So those are going to cause an acute inflammatory response. So kind of just reiterating this, we have our core antibody functions from the spec, which is well, firstly, antibodies can either be secreted, so they can be secreted by plasma cells, but they're also bound to B cells normally and act as a B cell receptor, enabling them to recognize, B cells as they circulate to recognize foreign particles. So the secreted form is then actually able to bind to microorganisms and prevent them entering cells. So we call this neutralization. We also have complement activation, which we'll move on to on the next slide. But then I want to focus more on kind of opsonization, which is a really key role, arguably one of the most important functions of our antibodies, because this means that our antibodies are binding to our foreign particles. And like I said, with the FC receptor, so this means my antibody binds to my foreign particle, then the FC region of my antibody is there. It's available for my phagocytes, such as neutrophils or macrophages, to then associate with that FC receptor. So that FC region, So once it associates using its FC receptor, it's then able to engulf and phagocytose the pathogens. So that's a really important function in terms of, we often use the term seeing the pathogen. So it just enables those innate immune cells to see the pathogen. The other important function is mast cell degranulation. And this is when it's actually really important to know the function of IgE specifically, which has a really high affinity for mast cell Fc receptors. So this means that IgE is normally essentially bound to the mast cell, and so the mast cells are basically waiting for the antigen to come along, and when it does and it binds to the IgE antibody, it leads to degranulation, which causes acute inflammation. We also have interaction with NK cells, which very similarly, we have the interaction of the Fc region with the Fc receptor on NK cells, and this leads to death of infected cells through the production of a lytic synapse. So now let's just have a look at a few Part A questions. I'll just give you a second on those. So we know that the antibody class involved in transepithelial secretion is actually our IgA antibody. Our immunoglobulins are secreted in large amounts by which cell type? That's going to be our plasma cells. This actually tripped a lot of students up a few years ago with putting B lymphocytes, but actually the secretion of antibodies is exclusive to our plasma cells, which differentiate from your B lymphocytes. Then immunoglobulins are plasma proteins which play a role in hemostasis, recognition of foreign proteins, stem cell proliferation or wound repair, and in this case it's B, recognition of foreign proteins. So finally, the last component of this lecture, we're going to have a look at the complement cascade. So at this level, you don't need to know too much about actually the complement activation and the process thereof, but you do need to know that there are kind of three different pathways. So we have the classical pathway, the MBP lectin pathway, and the alternative pathway. So these all result in complement activation. And what do I actually mean by that? By that, I mean that there are proteins circulating in the plasma which are activated sequentially in response to the recognition of microorganisms, and this then leads to these outcomes, including recruitment of inflammatory cells, opsonization of pathogens, and killing of pathogens. So let's just look in a bit more detail about how that actually occurs. So I have here kind of a little flow chart that, again, it's just another thing to write out a couple of times before your Part A's, and that will just help it kind of embed and you'll be really familiar with these different pathways. So the classical pathway, the mannose binding lectin pathway, and the alternative pathway are all just different mechanisms by which we produce a C3 convertase. So that's the kind of common outcome of all of these pathways. And our C3 convertase then produces from C3, which is a protein, it produces C3b and C3a. Then C3b is able to convert C5 to C5b and C5a. Our C5b then associates with C6, C7, C8, and C9, and that forms our membrane attack complex. So just going back to the functions of my complement activation, the membrane attack complex actually inserts into pathogen membranes as a pore. So it enables then the kind of pathogen is compromised because you're enabling all of the solutes, etc., to move into the pathogen and kill it. So that's how the membrane attack complex actually ends up killing the pathogen. But although that's kind of sort of the outcome I've highlighted from this complement activation pathway, all of these factors, C3a, C5a, and even looking back up at the top where we have our classical pathway and our mannose binding lectin pathway producing C4, if you can see at the top there, all of those factors are involved in different ways in the different functions of the complement pathway. So C3b and C4b are opsonins, which we know are involved in helping our phagocytes see our pathogens. And then C3a and C5a, so these are the byproducts at the C3 stage and the C5 stage. Those are both pro-inflammatory, so those act to increase the kind of vasodilation, so that we get recruitment of immune cells and other inflammatory factors, so that we can really launch a full immune response against whichever pathogen has invaded. So just to highlight the kind of spec points that you need to know from this, essentially you need to understand the process by which the three kind of different pathways that can activate this C3 convertase. You need to be aware that the classical pathway starts with C1, which is a circulating protein binding to a complex of antigen and antibody, whereas in mannose binding lectin, Mannose binding lectin essentially binds to a PAMP, which is a pathogen-associated protein. So it's just a protein that would be found on a pathogen. Then in the alternative pathway, we have hydrolysis of C3. So that just means that C3 is spontaneously hydrolyzed. That kind of draws us to a close then. I have one final part A question for you. So if you just have a look at this one for a second. So in this case, the portion of the immunoglobulin molecule that interacts with the components of the complement cascade is always going to be our FC region, because like we mentioned earlier, that is our constant region. And so in order to activate our complement cascade, we're going to require the constant region of our antibody. Okay, so that draws us to the end of this lecture.